We've discussed marginal probability, or the probability of a single event, and conditional probability, or the probability of an event given that another event occurs. We'll now use some rules of set theory to create new events from given events. The first operator we'll discuss is the intersection of events, denoted with an upside-down U. For event A and event B, the intersection is written as A intersect B. The intersection of events A and B means that A and B occur together. The intersection means AND. Let's take a look at events A, B, and C in sample space S. A intersect B is the overlap of events A and B, as A and B occur together at that overlap. Back to our deck of cards example. Let's say the experiment we're performing is pull one card at random from the deck. We can define event R as the card is a red card, and event F as the card is a face card. If so, what is R intersect F? That would be cards that are red cards and face cards at the same time, or red face cards. The set generated by A intersect B in this case would include jacks, queens, and kings of diamonds and hearts. The union of events A and B is denoted with A, U, B, and is read as A or B, or A union B. This new event consists of all outcomes that are either in A or in B or in both. Let's look again at events A, B, and C in sample space S. A union B includes everything in A and B, including their overlap. In the experiment, pull one card at random from the deck, event R is the card is a red card, and event F is the card is a face card. Here, R union F includes all red cards, including face cards, and all black face cards. What is the complement? It would include everything that's not R union F, or all black cards that are not face cards. Back to events A, B, and C. We note that events A and C are mutually exclusive. How would we characterize A intersect C in this case? We see that there's no overlap, no intersection of A and C. They don't occur together. As such, their intersection is the null set, or a circle with a diagonal line through it. If we take event R to be red card and event B to be black 10, naturally the intersection of R and B is the null set, as we can't draw a card that is simultaneously a red card and a 10 of spades or clubs. Another word for mutually exclusive is disjoint. Let's talk about some rules of probability associated with intersections and unions. First, let's say we want to calculate the probability of A union B. We said that the union generally means or. When it comes time to calculate probabilities, the union also implies add. Think about that. There's an additive nature to the statement, go to the store or go to the mall. We can do either, suggesting that we're adding those two ideas together. When we calculate the probability of A union B, we add the probability of A to the probability of B. But when we do this, we've double counted the overlap between A and B. That is, we've included the probability of the intersection twice. So the formula for finding the probability of the union of two events is the probability of A union B equal to the probability of A plus the probability of B minus the probability of A intersect B. This is referred to as the addition rule. Let's go back to event R representing a red card and F representing a face card, and find the probability of the union of R and F. We use the classical view of probability to find the probability of R as the number of ways R can occur divided by the total number of ways to draw a card from the deck. Half the cards are red cards, so 26 in the numerator. The total number of ways to draw a card is 52, which would be in the denominator. So the probability of R is 26 divided by 52. The probability of F is the number of face cards we can have in a deck, or 12, divided by 52. The probability of the intersection of R and F is the probability that a card is a red face card. There are 3 diamond face cards and 3 heart face cards, so the intersection probability is 6 out of 52. Therefore, the probability of R union F is 26 out of 52 plus 12 out of 52 minus 6 out of 52, which is equal to 32 out of 52, or 8 out of 13. That is, we have an 8 out of 13 chance of drawing a card at random that is either a red card or a face card. That's about 61.5% of the time. You're at a party this weekend and things are going a little slow, pull that one out to impress someone. Recall that a conditional probability is the probability that an event occurs given that another occurs. For events A and B, we said that the probability of A given B is the probability that A occurs given that B occurred. The way we calculate this conditional probability is with the use of the intersection of A and B. Let's motivate this with event R defined as the random card drawn as a red card, and event F as the random card is a face card. Let's say we want to know the probability of R given F. That is the probability that the card is a red card given that we know it's a face card. If we're calculating the probability of R straight up, we assume that the denominator is the sample space of 52 possible cards. But if we know that the card is a face card, we're reducing that set of possibilities down to the set F. We don't have to look everywhere in the 52 cards for the number of ways that R can occur. We focus on the overlap between R and F, considering the probability that F has already occurred. This calculation is the probability of R intersect F divided by the probability of F. Recall that the intersection between R and F has a probability of 6 over 52. The probability of F, the probability that we draw a face card, is 12 out of 52. Therefore, the probability of R given F is 6 out of 52 divided by 12 out of 52, or 6 out of 12, or 1/2. This should make some intuitive sense. Given that we know our random card is a face card, what is the probability that it's a red card? Well, half the 12 cards are red, so the probability that we have a red card, given that we know it's a face card, is 6 out of 12, or 1/2. Again, the idea with a conditional probability is to perhaps refine what we know about the probability of event A occurring, given that we know that B has occurred. In the case of the card example, the probability of a red card on its own was 26 out of 52, or 1/2. The probability of a red card, given that we know the card is a face card, is 6 out of 12, or 1/2. We didn't learn much knowing that the card was a face card. As it turns out, the events red card and face card are independent of each other, as the probability of R given F is just equal to the probability of R. Let's look at a consequence of the calculation of the conditional probability P of A given B, which is equal to the probability of A intersect B divided by the probability of B. Note that we have to assume a non-zero probability for event B, which makes sense both mathematically and intuitively. If event B isn't ever going to occur, if its probability is 0, then why do we care about conditioning on it? If we multiply both sides of the equation by the probability of B, we get that the probability of the intersection of A and B is the conditional probability, the probability of A given B, multiplied by the probability of B. This is called the multiplication rule, and it's how we can calculate the probability of the intersection of events. Recall that we calculate the probability of a union with the addition rule, and we said that union implies OR, which implies add. The intersection, on the other hand, implies AND, which implies multiply. The multiplication rule is particularly useful when events A and B are independent of each other. If A and B are independent, the probability of A given B is just the probability of A. Therefore, the probability of A intersect B is equal to the probability of A times the probability of B when A and B are independent. Let's use a little intuition to see why we multiply events together here. When A and B are independent, we are multiplying two numbers together that are both less than 1. What happens when we multiply two numbers together that are less than 1? We get a number that's smaller than either of the two original numbers. That is, 0.5 times 0.6 is 0.3. The more numbers less than 1 we multiply together, the smaller the resulting probability is. And that should make some sense for the intersection. When we have an intersection of A and B, we're saying that both A and B have to occur. Both occurring is less likely than either one occurring, or at most equal to one occurring. The probability of the intersection should be getting smaller. Contrast this with the union events, where either can occur to satisfy the union. There, the likelihood of one or the other is greater than or equal to the likelihood of any individual one. Adding events to the union makes the likelihood larger. We'll illustrate our new smarts with some examples from playing cards. What is the probability that a randomly drawn card from a deck is a heart given that it is red? We define H as the event the card is a heart, and event R as the card is read. And we look to calculate the probability of H given R. This calculation is the probability of H intersect R divided by the probability of R. Let's look at the Venn diagram at the intersection of hearts and reds. We see that hearts are contained entirely within red cards. So the probability of H intersect R is just the probability of H, or 13 over 52. The probability of a red card, P of R, is 26 over 52. Therefore, the probability of H given R is 13 over 52 divided by 26 over 52, or 13 over 26, or 1/2. We know for sure our card is a red card, so what's the probability that the red card is a heart? Half the red cards are heart, so 1/2. Let's switch that conditional probability around. What's the probability that the card is a red card given that it's a heart, or the probability of R given H? Again, the probability of H intersect R is 13 over 52 in the numerator. The denominator is the probability of heart, which is 13 over 52. Therefore, the probability of R given H is 13 over 52 divided by 13 over 52, or 1. That should make some intuitive sense. If I know that the card I pulled is a heart, then I can guarantee with probability 1 that the card is a red card, as all hearts are, by definition, red. One last card example. Let's find the probability that the randomly drawn card is a queen given that it's a face card. Event Q is defined as the card is a queen, and event F is the card is a face card. We need the probability of Q intersect F, or the intersection of queens and face cards. We see from the Venn diagram that queens are entirely contained within face cards, so the probability of Q intersect F is just the probability of Q, or 4 out of 52. The probability of F is 12 out of 52, or the number of face cards out of the total number of cards in the deck. The probability of Q given F is 4 out of 52 divided by 12 out of 52, or 4 out of 12, which is 1/3. The marginal probability P of Q is 4 out of 52. The knowledge that the card is a face card in advance changes the probability of drawing a queen to 1/3. We got a lot smarter about the likelihood of a queen being drawn by knowing that the card was a face card. That's one of the great things about conditional probability. It makes us smarter about the event of interest occurring, assuming that the events aren't independent of each other. On a different note, let's look at another way to calculate the marginal probability of an event that might be useful if we can't view that event directly. A marginal probability of an event is equal to the sum of all possible mutually exclusive intersections involving that event. This idea is best visualized. Let's take a look at events A, B, and C, along with another event, F. A, B, and C make up the entirety of the sample space, making them collectively exhaustive. Also, they don't overlap, so they are mutually exclusive. Now let's superimpose an event F on top. Event F is equivalent to F intersect A unioned with F intersect B union with F intersect C. Therefore, the probability of F is equal to the probability of F intersect A plus the probability of F intersect B plus the probability of F intersect C. This is generally represented as the sum of all possible mutually exclusive intersections involving the marginal event. For example, let's define R as drawing a red card, H as drawing a heart, and D as drawing a diamond. Naturally, the probability of R is the sum of the probability of R intersect H and the probability of R intersect D. 13 of the 52 cards are both red and hearts, and 13 of the 52 cards are both red and diamonds. Therefore, their sum is 26 over 52, or 1/2, the probability that the card drawn is a red card. We also know that the intersection can be written as the conditional probability multiplied by one of the marginal probabilities. That is, we just saw that the probability of A intersect B is equal to the probability of A given B times the probability of B. We can replace the intersection probabilities with this multiplication. That is, the probability of F is equal to the probability of F given A times the probability of A, plus the probability of F given B times the probability of B, plus the probability of F given C times the probability of C. This will become a useful property later on.